Hi, welcome back. In this lecture I want to talk about parallel computing with Python. I'm just going to give you a brief introduction. I will talk about threads and threads models in Python, and then I will anticipate a few words about the multiprocessing module and the task framework that I've been using for parallel computing in Python. So why parallel computing is one of the main optimization techniques to speed up our HPC code? Well, the reason for that is that modern computers have multiple CPU cores. De facto, all the processors that we've been using use a multi-core technology. However, traditional Python code that has not been parallelized runs on a single core. So if you want to go from a single core execution to multiple core execution, then we need some means to use multiple cores. Parallel computing enables faster execution on CPU-bound tasks. Basically, we divide our computational workload across different cores and we make the cores executing the code. So this is very good if we have something that is computational intensive. So for instance, some scientific task like matrix multiplication of dense matrices, or some visualization task. For instance, we have a filter applied to a pixel that is very heavy, then we can do in parallel on different pixel. So use very much in scientific computing for a CPU task or task where the workload is very computationally intensive, efficient handling of a large dataset when memory of the laptop or your computer is not enough. So we need to divide the data across different multiple memory system, and also is highly used in real-time applications. So if you want to run some code and also be responsive, then you might want to have a thread in order to take some steering from the user. Bottom line, also for this course, this is an introduction to performance computing. Parallelization is key for supercomputing and any high-performance computing system if we want to use them efficiently. In this course, we focus on two kinds of parallelism that you probably encountered before. The first one is a thread parallelism. Threads share memory within the same process. So the uniqueness about threads that you can have multiple threads, each one accessing the same memory. It's typically used for I/O bound task. For instance, if you have a network request you want to respond, you might have one thread just to respond to a network request, to handle file reading and writing while you're doing also other tasks. However, the Python has the problem of the GIL. We will say a few words later on. So in Python, multi-threading is often limited by this GIL problem. A different approach, instead of using threads, is to use so-called processes and process parallelism. This is to separate processes. So these consist of the fact that we run separate processes in parallel with independent memory. So each process has its own private memory, and it cannot access directly the memory of the other process. This is specifically used for CPU-bound task, and we are going to see in this course how to use the multiprocessing module and the task to use process parallelism. The picture you see here, we have a summary of different kind of parallelism. In this case is hybrid parallelism. We have two processes, even here, one here and one here, process 0 and process 1, and within a process with a spawn and handling different thread. So what is the characteristics of the threads? The threads share the same data. So in this case we have only one thread within the first process, and here we have three threads that share the same data, so they can access this data. So the particularity of a process is that fact that if we are on this process, we cannot directly access this data here on a different process. So we will need some technique, for instance, a message passing, to access that data on a different process. I'm going to say a few words about what are threads. I already introduced them, and also how we can use them in Python. The thread is a lightweight unit of execution within a process. So we have a process here with one and here with the threads, and the particularity that they share, the same code, data, and the files. So, for instance, in this case, we have 3 threads. They can all access directly to the data. Threads can run in parallel, but Python has the limitation that is called the GIL. So the GIL stands for Global Interpreter Lock, and this is actually a problem. It basically serializes our execution using threads. In summary, Python GIL allows only one thread to execute Python bytecode at a time. So even if we have a multi-core system, like we have here, only one thread runs simultaneously. So the Python threads take turns. So basically one thread, then they're basically sharing the same core. So the impact of GIL is the following. So thread works in well for IO bound task, but is generally very inefficient for CPU bound task, because the computationally intensive task is basically serialized. So when to use threads? Well, the previous slides tell you when to use it. They're good when we have IO bound tasks, but it's not really suitable if we have a scientific computing workloads and we want to use. Instead, we need to use a multiprocessing module and the task framework we're going to talk later. Let me say a few words how to handle creating and running threads in Python. See, here is a code explaining how we can start a thread. First, we declare t using threading.thread class, and then we start with the start method, and then we finish. We ensure the completion of the thread task by calling the join method. So the join basically blocks the code progress until all the threads are finishing. The way to define the task that the thread is actually running is to define here. When we define the class thread, we use target, and then here we give the name of the function that explicitly express the task. So the task in this case is to print the worker thread is running. So here we spawn one thread, and then as soon as the thread task is finished, then we can have a progress. So here we basically wait until it's finished. So we create a new threading thread, and we defined the task as a function, and we gave target equal to worker. We started, so the start execution on the thread, and then we join the thread. This ensure the main program waits for the thread to complete. Obviously, one thread is not very beneficial. We want to spawn our task in multiple threads. So how we do it? Well, we then here we create threads equal to bracket to bracket. So here we're declaring that we're going to use multiple threads, and then we are having a loop. In this case, we want to spawn 4 threads, and we do as before. We use a threading thread, and we define the function together with the argument. In this case is I. Is our counter. You see here the function has an argument. So when we spawn, we also need technically to append. So we do threads.append, and we start the execution of the thread as we did before by using a start method. Then finally we have another loop that is responsible to ensuring the synchronization before the program actually prints. So all the threads will be waiting here until all the tasks are finished before printing all threads are finished. So the GIL problem limits the usage of the threads in Python. So in the next few lectures, we're going to look at the 2 modules. So one is multiprocessing module, and then the task framework. This is the last slides of this lecture, and talk to you soon.